All right, so this is what it all looks like filled in. So you'll want to calculate the probability for each x value. So each x is the number of successful shots that Allison does, so successful scores. So the probability for getting none is, of course, very low. More likely for her to get close to 4 shots, maybe a little bit more successful scores out of 7 shots on the goal. Then we create this probability distribution graph out of that. Notice I did not make a nice even curve here because this is a discrete kind of population. So we have a very small probability of none up to around 0.2, 0.19 for her to get 3 scores on the goal. For her to get 4 goals, there's a probability of 0.29, almost 0.3. For Allison to get 5 goals out of her 7 shots, there's a probability of 0.26 and so on. And so we can create this nice probability graph. Another thing that I've done here is the expectation value. And you'll notice something just a bit weird about that. Our expectation formula looks a little different than normally it does. Normally it's x times p, right? I can't use that equation now, not because there's anything wrong with that equation or something has dramatically changed in the idea of expectation value. It's actually the exact same idea. It's just that we have a new definition for x now. We're talking about x here as being a successful goal. And that wasn't our definition of x in the expectation value formula. So we need to kind of redefine, move our variables around a little bit to make sense of expectation value. Expectation value is going to be the number of trials, like how many times does Allison actually shoot on the goal, times the probability of her getting in each time. So if she shoots 7 times and there's a 0.6 probability every time, we're going to expect her to get 4.2 goals. And that's kind of what our graph shows too. So somewhere just a little bit above 4 is what we're expecting for Allison's goal scoring. Just another example, you might see it phrased as sort of a defect probability. So for gummy bears, there's maybe a 5% chance of a manufacturing defect. You know when you get those gummy bears and they are missing an ear or something, they look kind of funny. So there's a 5% chance of that in a single gummy bear. What we want to know is what's the probability of getting exactly 4 misshapen gummies in a box of 38 gummies. So let's see if we can figure out what our x, n, p, and q are, and then we can sort out the probability of getting exactly 4 misshapen gummies. So x is the number of successes. In this case, success is actually getting a misshapen gummy. So we're looking for 4 misshapen gummies. N is our number of trials, and here it's a little different from like consecutive trials, shooting on a goal or something like that. Our trials is actually, well, how many gummies are in the box altogether, and that's 38. The probability of a gummy being defective is 0.05. So that's actually a probability of success here because we've defined success as getting a misshapen gummy. So the probability of that success in a single gummy is 0.05, and Q is the probability of a normal gummy. So that would be 1 minus 0.05 or 0.95. So it's the probability of failure. In this case, we're defining failure as being getting a regular old gummy. That's kind of boring. Okay, so the probability of getting exactly 4 misshapen gummies is going to be our 38, choose 4, 38, choose 4, times the probability of a single gummy being misshapen, 0.05, to the power of x, the number that we want, 4 of them, times q, 0.95, to the power of n minus x, so 38 minus 4, or 34. Toss that all into your calculator, see what you get. 38, choose 4, times 0.05 to the power of 4, times 0.95 to the power of 34. And I get 0.08. So there's an 8% chance of getting exactly 4 misshapen gummies in a box of 38. Just to maybe harp a little too much on the expectation value, make sure that you write it down as a formula somewhere so that you remember x is not the same as the x's we've been using in our expectation value. So when you're doing this kind of binomial distribution problem, you need to redefine your expectation value to be n, the number of trials, times p. This is exactly the same meaning of formula. We're just being careful because x now means something different. Now x is about success. So just as an example here, in our case of the gummies, there's a 5% chance of a single gummy being misshapen. How many misshapen gummies do we expect in a box of 38? Well, we just take n, the number of trials, or in this case the number of gummies in our box, times the 5% chance for each gummy, that's p, our probability, and we're expecting around 1.9 gummies in the box to be misshapen. All right, so that is binomial probabilities in an